So the main objective today is to follow our computational study. Last time we managed to generate Gaussian inputs and to run the calculations. Now the question is, how do we know if the calculation reached correctly the end? We know that the computational work is done, there is no more computation, but did it fail? Did it converge? How can we do that? And then, if this is called a quality check, if the quality or if we are quite sure that we reach the correct results, how do we extract and format the results from the log file? For those who've been in the Master 1, we've discussed a little bit this point, but the question is now, how can we be sure that our calculations reached the end correctly? What do you propose? What do we have to check?
Maybe the program is giving us some answers and some codes of correct ending and not correct ending.
Indeed. So I will go to the results of the Bolton's article compound. Okay, so you have the logs. However, if you have a virtual machine with a Linux, you can copy what I'm doing. If not, you need, for example, to open the log file with Word, maybe, or WordPad. Beware, for example, if you open the log, it's more than 100,000 lines. Okay, so it's quite huge. With Linux, we have tools to manage, and we can easily treat such a type of long files. So if we go to the end, Gaussian usually put as a last line a normal termination. Okay, that means that for Gaussian, he managed to go until the end. And if there is an error termination, that means that there is a problem during computation, and he managed to an error stage before shutting down. If there is no error, neither normal termination, that means that the program crashed during calculation, or is still calculating. Okay, so you should have a termination to indicate that Gaussian reached the end of the process. If there is a normal termination, Gaussian thinks that everything went smoothly. Beware, that does not mean that he reached the correct destination. He just managed to do the task until the end. I've met some experimentalist colleagues that check if there is a joke in the end, and Gaussian used to put some citations in the end. That does not mean that your calculation reach the correct geometry, for example, or the correct states. That just indicates that you have a normal termination. Okay, so if you have more than one log file in your directory, you can use the grep tool in Linux. It's like a find. He will search for normal termination in all the log files of your directory if you want. So here we've done 4 calculations: frec, OPT, TD, and TDD, TDT for the triplet states. Okay, TD is singlet states, TDT triplet states. And today we'll be doing some quality check on those 4 files and to learn how to treat the results of those calculations. That means how to have a spectra, how to have information, okay, with Gaussian, with Windows tools and Linux tools.
Okay, that I have 3 files, 3 log files.
Yeah, because
frequency, OPT, and TD.
Exactly, because you didn't ask me for the triplet states.
So from this one, I can get some luminescence or not?
No, you have absorption.
Only absorption.
Yeah, but okay. So
because you said that at first maybe we have to try absorption and from that point try the emission.
Exactly.
Because you said the molecule is very big.
Today, the secondary objective is to check if your calculations went smoothly, if you agree with the results. That means that your functional and basis set give you the correct expected results, okay? If you need to launch it again or not. Then, if everything is correct, you can launch more calculations. For example, the optimization of an excited states for luminescence, okay? Or maybe another geometry, or maybe a substitution, okay?
Okay.
When you have several jobs on the same molecule, like here, OPT, frec, and TD, what do we need to check?
Maybe we can check that we don't have an imaginary frequency.
Okay. For frec, imaginary frequency. Okay. So here, let's start. It's not what I expected, but never mind. It's an interesting answer. So here in the frec, we should have frequencies. Okay. So if you grep frequencies, you have different lines with the wave numbers for each frequencies. If you want to see it in, if you have opened the frec.log, you can search for frequencies, and you will see that almost in the end of the file, you have all the normal modes, the symmetry, the wave number, and the atomic displacement XYZ for all the atoms. and if you do a grep frequency, you only get those lines. And this is the lowest wave number. It's the first normal mode computed. So if this value is indeed negative, you have an imaginary frequency. Look, you can see just below, just before, that there is like low frequencies, and there is a -5, -0, -0. So if the computation gives some low frequency, it discards them. That means that if you have here a minus something, for him it's not a low frequency. It is, for example, those 3 here does not count. For him, the first wave number is 77. That means that if you have like -50, you have a low frequency. You have a negative frequency. If your first negative here is like -10, that means that you have a small negative frequency, and maybe we could talk about the numerical imprecision. When you're doing some calculations, you have integrals, you have a grid, you have numerical errors, and maybe -10 in frequency, you are almost at 0. So we could discuss. If you have -50, -100, clearly you have a negative frequency. Okay? So
I don't get it.
Yeah. In the frequency calculation here, if you are at the bottom, you have only positive vibrational energies. If you are not at the bottom of your energy, that means that if your atoms are not in the best position, if you are not in a global minimum energy, you will have maybe 1, 2, 3 negative energies. If you have 1 negative energy, that means that in this mode, you are not in a minimum of energy, and your optimization did not converge to a global minimum, but it converged to a transition state.
Okay, so if I have at least one
Yeah.
negative, then I am not in the place I want to be. So it took me some state, but not the lowest one.
Yes. However, maybe sometimes you will want to search for transition state. So if you're looking for a global minimum, and if you have an imaginary frequency, no, you didn't reach the state that you were looking for. If you have an imaginary frequency and just one, and you were searching for transition state, it is a good result. Okay? Here, we want, when we do an optimization here for ground state, we want all positive normal modes, and this is what we get. So we are in a global minimum.
Where can I find it? Like if I am working from Windows, I'm not so.
You can open your frec.log.
Yeah.
Okay, and you
I opened it in Notepad.
Notepad. Oof. Okay. Yeah. It's quite heavy maybe for Notepad, but if your computer manage,
it's okay actually.
Okay.
I don't know.
Okay, perfect. You can search for this word, frequencies, with an F caps, okay, and in plural. and
Okay,
and the
frequency.
and the first occurrence should be the first 3 normal modes.
Okay, I'll try. I don't know if in yeah, 90.
But however,
Frequencies.
I've told you that we will be starting with checking all together the same compound, okay? Not yours, but the same compound, so you can get the same answer as me. So you are sure that your procedure is correct because you know the results, okay? And then when you know how to do it, you will use it for your compound, okay?
Yeah, but I can't find actually frequencies in my freak dot log. I don't know why.
So with your compound,
I don't know, maybe I am doing something wrong.
yeah, that's why I told you to start with a bolt-on. You check for the frequency and you should have 77.
77. Okay, I'll try with Bolton frequencies.
So you open the frec.log and beware F in caps, okay? And
I can search with register and without register, I suppose. Yeah, here I see like 77, yeah.
okay. So for your frequency, the first line should be 9.9, 18.9, and 21.1. There is
for my compound.
Yep.
Oh, for my compound in frec.log I can't find actually the word frequencies. I don't know why.
Either you wrote frequencies bad, or maybe the file is too huge and it doesn't manage to open everything.
Actually, like I see the word normal termination, and I searched frequencies in like Bolton file. In Bolton file, it worked. Actually, I tried the same word. I copied the word that I used in the Bolton file.
Yep.
But in my compound, I can't find it.
Okay, I do find frequencies in your log file. I think that okay, let's see. If you want, we can use we can check with a graphical tool, okay? So maybe there is like GaussView that can open a result from Gaussian. However, GaussView is not free. There is Avogadro and there is Gabedit.
I have Avogadro.
Okay, and I think that with Avogadro you can open the frequency file and it will give you the normal modes.
Frequency ENP?
No, log.
Log. I have to open it with Avogadro.
Yep. By the way, to check graphically how the optimization worked is a good idea. That means that if you have Avogadro, Molden, Molecule, GrapEdit, GussView. There is more than one solution, and you can see the geometry and you can see the converged structure. I think it's interesting to check it. You can always check the quality of the geometry. Okay, so here I'm using Molden in Linux, and I can do an animation to see what happened during the convergence. Okay, so here, for example, for the bromobenzyaldehyde, it's really a small molecule. There were only 1, 2, 3, 4, 5, 6 geometries computed, and he obtained a converged compound. And when you look at the structure, it's a structure that is chemically reasonable. It seems to be what you expect. Okay?
Okay.
So it's...
I opened it in Avogadro. I see the frequencies.
Yeah.
The frequencies start at 995. Is it correct?
Yep.
Okay, so I can see on Avogadro these frequencies, and
okay.
It's okay.
Okay, for those who want to do the same, you see, you can download Avogadro, for example, or GrapEdit, or and you will see the frequencies. And you see the geometry. So you can look at the geometry of your frequency, and you can see if chemically it represents or it corresponds to what you ask at the first stage, okay, before the optimization.
Am I correct that it is what I see here in Avogadro? It's optimized version of my molecules that I pushed to calculations.
Yes. If you open the frec.log, it is the results of after the optimization. That means that first we do the optimization, then we copy the geometry and the wave function to the frequency calculation, and the frequency does not move anymore the atoms. That means that what you see in your frequency calculation log, it corresponds to the finish of your optimization. If you open the OPT, for example, we can, if we open your optimization with Molden, we can see the evolution of your geometry during the optimization, but only in the opt.log. Beware, there is, for example, in GussView, when you open the opt.log, you only see the final geometry. So not all programs can show you the evolution of your geometrical optimization.
I see that OPT file is harder to work. Why it can be like? So in frequency we have already the frequencies for optimized molecule, and here.
So here in the frequency, for example, in your frequency.log, the log file is around 1 mega. And your compound, your optimization.log is 89 megabytes. Okay? So it's quite huge. That's why, depending on your memory RAM size, it will be harder for the program to open. So in my screen, okay, I've opened your geometry. So this was the starting point, and we see the evolution of energy. So this is the total energy that goes down. The forces is the interaction between atoms, and the steps is the evolution of the quantity of the atom displacement at each step. So usually at first he moves a lot the atoms, and then it converges to small atomic displacements. And you can see here.
Can I see it in Avogadro or only in
I don't know.
your program?
I don't know if you have the cinematics in Avogadro.
Because actually I don't see it. I see only orbitals now. And that's all for
I don't use a lot Avogadro, so I don't know. Maybe. What I can say is that, you see, at first we had something with like a penta-coordinated, and with a movie is now or it was more tetrahedral, and now it's clearly square planar. So it's quite drastic. So now you can compare this geometry with your X-ray, and if it's quite different, maybe we can start again, or maybe in gas phase the geometry will not be the same as in solid state. And it could be due to packing, to intermolecular interactions in general.
I'll see now. Okay.
So here, when we have several jobs of the same molecule, we need to check if it's the same geometry. That means that here we have several geometries. For example, in your optimization, you have more than one nuclear repulsion energy. So the nuclear repulsion energy is the quantity of repulsion based solely on the nuclear positive interactions. So it's a repulsion. So it's a nuclear repulsion energy. Each time that you change a little bit your geometry, you will have a change in the nuclear repulsion energy. So you see that there is 1, 2, 3, 4, 5, 6 different energies. The last repulsion is this one, and you can see that it's the same repulsion in the TD, TDT, and FREC. That means that our computational procedure went correctly. That means that he has done an optimization and he gave the optimized geometry to the time dependent and frequency calculations. So here we can say same geometry, nuclear repulsion.
Okay, so if we have the same nuclear repulsion for different log files, then we have a normal calculation.
No.
No?
No, it does not mean that we have a normal calculation. We've checked if there is a normal calculation, okay, a normal termination. What we can say is that the procedure went correct in this part. That means that you are really doing the frequency calculation and time-dependent calculation of the geometry that you think is a global minimum. If in your frequency you have no imaginary, that means that indeed it is a global minimum. So with OPT and FREC, if it's the same geometry and there is no imaginary, you can say it is a global minimum in energy. Beware to check if it's the same functional and basis set. So we need to check if there is the same number of basis functions. Non, on va chercher primitive. So you can check for primitive. It's a Gaussian primitive, or you can check on basis function in plural. And you see that in the optimization, in the TD, in the TDT, you have the same line, 402 basis functions, 611 primitive Gaussians. Okay, so that means that you have the same number of atomic functions. So probably it tells you that you have the same basis set. So now we have normal termination for all your logs files. You have the correct change in nuclear repulsion, then the same nuclear repulsion between the files. You have the same number of basis function. Okay. So now
you are searching for primitive in also in frequency.log.
Exactly. In all the log files to check that the basis set between the different log files is the same.
I don't know why, but actually I can find even primitive in log file.
Primitive
even in Bolton.
Primitive in singular.
Yeah, in singular. And starting from the lower. Yeah.
I do find primitive in your log.
Actually, I tried to find actually even in Bolton, not only in my file. I don't understand what is happening. Maybe it is connected with that I'm working from the notepad, but I don't know. I have difficulties to find it. I feel very strange about it.
How do you find it? How do you manage to do that in a directory? You open in Notepad?
I open in Notepad, and in Notepad I have Control F, like find. And then in find I search for words. When I was searching in file Bolton for frequencies, I found them. Yeah. In frequencies log of these compounds that you are explaining, like the simple compound.
Yeah.
I managed to find frequencies, but in my file I haven't found them. And now even in Bolton I can't find with that way I can't find primitive. How many lines do you have in the files?
In which one?
I have in one 1058 and in other 11,502.
in the frec, I have 1825. In the optimization, there is 137,227.
I'm not sure, but maybe we have the different number of lines. Maybe notepad some not showing it correctly.
So here I open with notepad plus the frec.log, the Bolton, and I do primitive, and I find it. It's line 626.
Can I don't know if it will bother, but I can show
No,
how I make it. And
can you open your frec.log of Bolton and
frec.log?
Yeah.
Okay.
And you go at the line 626. If your notepad do
I have the simplest notepad actually.
Okay, so this one is free, Notepad++, and is really great.
Maybe I'll download it. You said what line?
626.
I found 326. I have like 402 basic functions.
Basis functions, yeah.
Yeah. Primitive Gaussians, yeah. I don't know why it haven't found it me earlier. But on 626, I see the word primitive.
Okay, so either you wrote maybe you wrote primitive bad, or maybe
you know, I copied this word primitive, and then I tried to find it, and it doesn't find it, even when I copied it from this document.
Okay, so that means that your notepad is only looking in what he can manage to get in the maybe in temporal memory. I don't know.
Okay. So you suggest me to use to download Notepad++?
Yeah.
Or what?
I think Notepad++ is excellent. Is an excellent notepad.
Okay. I'll try to find it now.
Okay, so now we know that we have all calculations, normal termination. All calculations, same geometry in the end, same basis sets. Okay, you can check the functional, you can check the formula, the stoichiometry, for example, if it's the same brute formula. We can check in 3D, in graphical visualization, the geometry, if it seems to be correct. Okay, if you've done all this, it seems that everything went smoothly. Okay, so everything went fine. So I will be checking on your compounds. So let's start, for example, a first illustration with the group AKT. you've done a first geometrical optimization here for your molecule 1. And
Yes.
and we had a frequency normal termination, TD normal termination, everything normal termination. I open with Molden. So here we have this compound, movie. Okay, so everything seems to be fine. However, it's purely planar. And if I do if I check the frequencies in your frec, I have 3 negative frequencies. Okay, so for example, if you use a graphical program, maybe you can have an animation of your negative frequencies. It works with Molden. I know that Gabetit does it. Probably Avogadro too. That means that you open your ER spectra, and here you click on your you select your negative frequency, and you see the vibrations. And what you see is that the benzene that is at the that do the bridge, okay, is doing an oscillation that is an out of plane oscillation. This oscillation, if he does it, it will stabilize the energy. That means that your compound should be more stable, if not planar. And here, your first input was a totally planar compound. He used a symmetry plane, and he forced the compound to be planar. So everything went correctly for Gaussian, but if you're not looking for details, you could miss this small details that Gaussian went smoothly with a condition is that to keep the molecular as planar. And the problem is that you didn't ask specifically to have a planar compound. It's just that by default Gaussian, when he see a symmetry plan, he force it. Okay, so you have just to change a little bit of the geometry, and you break the planar symmetry, and you obtain with it's what I call the Mol1 3D, a frequency that is this time all positive. So now you have 2 versions, okay, of your compound, and you can discuss the planar effect of your geometry on the frequency and on the excited states, by the way. So the fully relaxed, that's what we call fully relaxed. That means that you don't have any constraints. Here, your compound is clearly not planar. There is this benzene that do an angle, or that maybe there is a geohedral angle here that's almost 50 degrees, and there is also a dihedral angle in this benzene correspond in respect to this double bond, and this double bond in respect to the benzene. So clearly you have a torsion in your compound.
So basically, the good molecule is the mol1 3D, the non-planar one. And we must discuss why is it the good one, if I understand well.
It's the most stable conformation in gas phase is a compound that is not planar. That does not mean that in materials, in solid states, the planar form will not be more representative of the expected or measured properties. You see?
And can we do computing stuff with the solid state or not?
The thing is that indeed, when you want to compute a geometry that is more like a solid state geometry, but without the explicit interactions, you can use symmetry to force, for example, a planar state.
Okay.
If you compare the CPU time for the optimization in the planar, it's 5 days and 10 hours. In 3D, it's 7 days and 17 hours. But for example, for the frequency, there is like 6 days of differences.
Okay. And
for the TD, it's not.
It's an AIE molecule, so it aggregates. It forms a very emissive aggregate at the solid state. So I think it's more interesting to work with this molecule, with the calculation of this molecule at the solid state. I don't know.
We'll see.
Yeah. Okay.
You have both, so you can compare.
Okay.
Okay. So if we look at one problematic compound, so there is only one compound that did not fully converge. Okay, is the polyoxometalate. What a surprise!
Not really.
But I did manage to compute a geometry, and thanks to the second sieve that you sent me, okay, and some transformation. So I will show you what happened, and we can all discuss what is the problem and learn from that. And the first problem is in this kind of inorganic compound, what can we define as a molecular entity is important. So if you use Gaussian, you need a molecular entity. So the formula was 1 antimony at the center, 6 tungstens around, and 6 oxygen all around the coordination of your atoms. So here in the center, the oxygen are shared between 2 tungsten and 1 antimony. So all the oxygen of the antimony are shared with each 2 tungstens, and then we have 1 oxygen that is a bridge between 2 tungstens. The other one here is also shared with the antimony, The two here are shared with the antimony, and so for X tungsten there is 2 oxygen shared between 2 tungsten, and there is 2 oxygen that are only coordinated with 1 tungsten. So if we look at the charges, because in your formula what you've given me is that you say it's a -1. The problem is that antimony redox state is generally +5. Tungsten can be +4 or +6. And usually oxygen in the oxo states is -2. So that means that here you have 24 oxygens. That means 48 minus. You have +5 for the antimony. And if you do a tungsten that is +6, you have a +36 +5 +41. That leaves you with a -7 charge. And it corresponds, and it managed to compute. So you have this small piece of POM, and you have a total charge of -7. That means that there is like quite a few LUMO that are occupied. Okay, that means that you have a high energy, high moleculars that are fully occupied. For the optimization and frequency, no problem. You have FREC and optimization, no problem. And by the way, here I've let you an old optimization just for the others to see that sometimes you have an error, and if you are an error termination via link 502, I will copy that in your
Can I ask, can I download the Molden that you are using? Like,
there is a Windows version, but is more recent, and I'm not sure that it's working in Molden in Windows.
Mm-hmm.
Because there is a new one and there is an old one. It was totally refounded, and okay, so this is the old one, and it does, yeah, there is an updated to Molden version 5.8.2.
Mm-hmm.
So you can try.
Mm-hmm. Okay. I suppose, is it free, yeah? For academic purposes?
Exactly. So the Gaussian errors, they will indicate a link and with an application in an exe file. That means that with your L502, you know L502.xe means an SCF error. So if you have a Gaussian error, you can check for error termination via link, and you copy this part, and it will give you some information on why did it fail. So here it was an error in the convergence on the first wave function. So for those who are a little bit familiar, if you do a grep down star log, you have the SCF done. This is the total energy of the electronic part, and you can see that you have one energy for each geometry. But here, for example, you see that you have this energy. OPT1 was the first try, okay? So it's this energy after 129 cycles. Cycles of self-consistent field energy. You give the atomic orbitals. He is doing a linear combination of the atomic orbital. He is trying to optimize the best wave function, the best molecular orbitals, to minimize the energy without moving the atoms. So this is the SCF part, to obtain the best geometry, the best energy for one geometry. In an optimization, you will repeat this process until you find the best geometry with the best total energy, with the best total wave function. If you compare to our Jablonski diagram that we drew last time, no, we didn't draw it. Okay, yeah, here. Here, it was the ozone part. We have a starting geometry, and here we optimize, or we minimize the energy with this geometry. And this is the single point, the energy minimization, or the SCF process. If it fails in the L5002, that means it does not manage to get a correct molecular orbital in 129 cycles. Maybe you can give him more, but you can see that when your system is correctly defined, generally you don't need 129 cycles. You need much less. So the problem here was I set a charge of -1. That means that there were 6 electrons less than I've selected in the end, because I followed the molecular formula that I was told. And the calculation cannot manage to get a wave function with this charge. Another possibility is that you are missing one hydrogen or 2 hydrogen, for example. So if you're missing something and it doesn't manage to get a correct wave function, it may be crash, or not crash, but it will end with an error termination of L5002. It's probably the most common error when you're doing a Gaussian. or it's the most common error with a long-term error termination. That means many times you will have an error before that crash directly because the basis set is not correctly defined, because there is a problem in the geometry that is clear, because you don't have the correct spin multiplicity. Those kind of error, it's an L300, 401, 402, they crash immediately. That means that the program ends rapidly. This one, there is an SCF process that is quite long because it's 129 cycles, so it's an error that goes far. You take time to have this error. Another possibility is that he managed to get a wave function and it does not have a correct geometry, he thinks, so it's an L9999 error. But I don't think that I didn't see one here. And in the TD, so we can open the TD, you see you have an error termination with an L101, 801, 801. And this is the TD part. Okay? So if we open the TD, you have sometimes more explicit answers in the error here. But we have here inaccurate quadrature in calculations of integral sum. And the problem here, probably, is that you have an atom, 74, and you have a problem of grid. So our atom's 74. No, it's the atom with an atomic number 74. So it doesn't like the wave function for the tungsten, and it doesn't manage to use it for calculation of the excited states. So here we have an optimized geometry. We have a global minimal state with a frequency, but the TD DFT don't manage to compute because probably there is too many electrons around the tungstens, for example. Maybe. So what I've done is that I try to compute with a bigger basis set. The problem is that with a bigger basis set, you have quite a lot of atoms, quite a lot of orbitals and integrals, and it's too big. So if we want to do that, we need to find a basis set special for the TD-DFT for this kind of thing. So now my question is, do you have some indication of what others have done for time dependent for POMs, for example? So if you have looked at the literature and there is some calculations, we could get maybe another functional, another way basis set to change and to treat this compound.
I will check because I have a paper on it. So
okay. So when you have time, you check and you tell me, and I try. Okay. So now
okay, thank you.
You have geometry. You have the frequency. However, we have a problem for the excited states. Okay, I think that. before making a break, I would like to show you a program that we've made in Angers. One of my axis of research is to be able to generate automatically a molecular report that check what we've see, that if it's the same formula, if it's the same functional, basis set, nuclear geometry, nuclear repulsion energy, total energy. Can we say if our log files correspond to the same molecular entity, and can we extract automatically the results? So it took me like 5 years of programmation. Not only we started with a small internship in computational science. I used 2 master internships in the first part of the program with Johan Morey, that is a computational engineer, scientific computation engineer in Moltec Anjou. And then I met with Benoît Damota, that is a real computational scientist, computational science and data science. And we've started again from scratch. And 4 internships later, we have something that is quite efficient, I think. So it's a Python programming. It's not available now. You cannot download it. But I would like to show you. And for the Akati CTR and ELW, you have the reports that are generated and the pictures. And I wanted to show you how it is done. No, I'm not in the correct. Yep.
So these pictures that we see, they were generated by this program.
Exactly, and I will comment why for you it crashed, and I still don't know why, but it will. I have to check why it didn't work for you.
It crashed?
Yeah, I will show you. So okay. My program is called quchemreport for quantum chemistry reports, and we have to give him the list of the logs, and he will check the quality of the logs, and he will construct the orbitals pictures. So it's a Python program. So Python programming is really interesting. Is really an efficient program. We have a Qt graphics for and matplotlib for the graphics. So we check if there is the same formula. Okay, so we have the same formula. We check if we have the same functional and basis set. Indeed. We check if we have the same conformer, geometrical resolution, geometry in 3D. Check the same charge, check the same multiplicity, and now we are generating the pictures of the HOMO -1, HOMO, LUMO, and +1 for the reactivity and so on. And we calculate the density then to have the electrostatic potential. That means the we map on the density the positive and negative electronic charges. So we see the delta plus and delta minus in the density. Beware that these pictures are quite experimental because we do a convolution, and it's take these pictures not for granted. There is maybe there is some tricky parts here, but the rest is correct. So we've done the pictures. We will be doing the why is it so stuck? Okay, should be faster. And then so the biggest part is the electronic static potential. So it took me like some seconds, but for big compounds it can take me several minutes. Okay, because we have to make a discretization of everything. So he used LAN L2. Oof. Okay, it's an awful difference. Okay, so the difference between A, B is the diffuse function. Okay, so LAN, L2, DZ, and PD, that he had some diffuse function. And for the third one, instead of a LAN L2 DZ for oxygen, he do a 631G DP for the oxygens. Did he manage to get a TDM time dependent with this?
No.
No, because this is a wave function. This is a functional that is efficient for geometry, sometimes thermochemistry, but for excited states, not so much.
And they only do for electronic properties and vibrational frequencies.
Okay.
Not
okay. So please try to check if you can find some people that have done some TDDFT on small pumps, and tell me what kind of functional and basis sets they've used.
Okay.
After the electrostatic potential map, the program calculates the electronic density differences between the excited states. And for the singlet and the triplet states here. So this picture we've discussed is in last year, and I will present it to the new ones today after the break. And it's an interesting tool to discuss the electron movement during excitation. So the second part, we will discuss what are the results that you can present, and for example here we will try to get the Jablonski diagram or discuss the result comparatively to the experimental data, for example. So we'll let the program finish alone. So it's break time, 10 minutes, a little bit more, and we start the second part. Okay? See you soon.